All right. We're in a boat in the ocean. And let's say your boat has a motor, and the boat can generate 20 miles per hour of velocity in whatever direction it's facing. So if the boat's facing this way, it can generate 20 miles per hour that way. If the boat faces some other direction, this way, it can generate 20 miles per hour this way. If the boat faces this way, 20 miles per hour. All right, so depending on whatever direction the boat faces, it can go 20 miles per hour in any direction. We're just gonna hang out and we're gonna be in the ocean. Pick a direction, you go 20 miles per hour in that direction. Okay, so that's what the boat can do. By itself, the motor generates these force vectors. However, and we're gonna lose the water here. Let's say that there are a number of different forces acting on this boat. And it doesn't matter how many there are, because at the end of the day, they all can combine into one force. So let's say there is a current, and let's say the current's going this way. So all that water is flowing this way. Let's place the boat at the center of a coordinate system. And let's define north, south, east, and west. And let's just say that our boat is at some center of some coordinate system with north, south, east, west. Now we can say perhaps that the wind is, or sorry, not the wind, the current is flowing from west to east. So we can add a current vector right here. And let's say the current is flowing at 6 miles per hour. So the current vector would simply be 6, 0. Let's say it's just going perfectly west to east. Let us say that we have a wind vector. Okay. And let's say the wind is 10 miles per hour, and let's say that it is south 20 degrees east. Okay, so I can find a wind vector here. And I want my vectors in component form because they're much easier to work with there. If this is 20 degrees, this is negative 70 degrees in my coordinate system. So the W is equal to 10 cosine negative 70, 10 sine negative 70. Process that for a second. I'm going to grab a calculator and actually turn these into decimals. Okay, so we're going to do 10 cosine negative 70, which is obviously a positive value. I'm seeing that it's about 3.42. And I am going to do 10 sine of negative 70, which is obviously a negative value. 10 sine negative 70, which is equal to about, we'll just call it negative 9.4. Okay, great. I've got current, I've got wind. Okay, we can introduce all kinds of crazy vectors. Who cares? Let's say that the moon is exerting a gravitational pull, moon force on the boat. Let's say the direction of the moon force is north 10 degrees west. And let's say the moon force is 2 miles per hour. So here we go, moon force. And the moon force, call it vector M. Well, this angle would surely be 100 degrees. So it would be 100 cosine, nope. Its magnitude is 2. It would be 2 cosine 100, comma, 2 sine 100 degrees. So we can evaluate that, and I will. We can evaluate our moon force. Let's do 2 cos 100. And we get about negative 0.35. And we will do 2 sine 100. We'll get about 1.97. Great. Oh, and guess what? A pack of dolphins just showed up, and they're going to start pushing your boat because the dolphins are playing around. So we're going to have a dolphin force. Dolphin force is going to be south 30 degrees west, and the dolphins push, they're pretty strong. They can push at 3 miles per hour. So we're going to add this dolphin force. South 30 west, it's a 30-degree angle here. That means this angle is 210 degrees. So our dolphin vector is going to be 3 cos 210, 3 sine 210. Great, I'm going to evaluate that. 3 cos 210, it's equal to negative 2.6. We would expect it to be negative. It's in quadrant 3. Sine, we should expect to also be negative here. 3 sine 210, negative 1.5. 30, 60, 90. Probably could have figured that out. Okay, so negative 1.5. So there's our dolphin force. And if we want, we can keep adding more and more forces. But the reason we're putting all these forces, and I'm trying to illustrate to you, it does not matter how many. We could add 10 more forces to this situation, right? What you want to do is get your forces as components. And then add them all to get one net force. So all this stuff is all in the environment. We've got wind, we've got current, we've got moon gravity, we've got dolphins, we've got all kinds of stuff acting on this boat. But the beauty of vectors is we just add them all up and we get one net force. So all we have to do is say, we can take our current force plus our wind force plus our moon force plus our dolphin force. We can add all this up. So we add 6, 0, we add 3.42, negative 9.4. We add the moon force, negative 0.35 and 1.97. And we add the dolphin force, negative 2.6, comma, negative 1.5. Okay, by the way, draw a dolphin on the top of your page tomorrow on the test. I'll give you plus 1%. Make it a nice dolphin. Practice tonight. Dolphin, 1%. Okay, we add these up. I'm going to put on my calculator. 6 plus 3.42 plus 0, plus negative 0.35 plus negative 2.6. Add those up. All right. In vectors, adding vectors is easy because you just add all the components. You add all the x's, so all my x's get added, get a new x, add all my y's. 0 minus 9.4 plus 1.97 minus 1.5. Okay, we get negative 8.93. Great, so I can just take all my y's, look at my y's, boom, add them all up. And this is great. I get a net force. Net force. All of these things are happening to the boat, right? All of these things are happening, just environmental things, but altogether it produces a single result. 6.47 comma negative 8.93. So the effect of all these vectors, all these different force vectors, is simply something in quadrant 4. We get some force altogether in quadrant 4. This is the net force. And it's 6.47, and it is negative 8.93. So if we add all these vectors, we should get this result. And this net force, I'm going to draw a new north, south, east, west for this, but this net force has a horizontal component, and it has a vertical component. North, south, east, west. Here's my net force. 6.47, comma, negative 8.93. Okay, which means that my net force acting on the boat here can be broken and thought of as a horizontal component, 6.47, comma, 0, and a vertical component, 0, comma, negative 8.93. This is essential. We have, this is the result. If the boat just hangs out in the water, it's going to start moving this way, which under the backdrop of north, south, east, and west is 6.47 miles per hour east, negative 8.93 miles per hour, or 8.93 miles per hour towards the south. So if I don't do anything else, this is what my boat's going to do. okay? No matter how many forces we have, it could be just the current, it could be current and wind, it could be current, wind, and dolphins, and the moon, and the sun, and the rotation of the earth. Just add them all up and you'll get one resultant vector. It is the net force. It is what's happening from the environment to the boat, independent of what the boat does. So this is the environmental force acting on the boat. Now, as the captain of this boat, and you are a boat captain, you can pick a direction to point your boat and drive 20 miles per hour with velocity in that direction. So, say you are to point your boat directly in the same way that the current and the moon and the wind is going, well, then you're just going to go way faster, right? You're just going to go, like, you're going to get completely enhanced by all these environmental forces. Alternatively, if you point completely opposite to it, these forces are all, like, you're going to slow down a lot. So, and then, in fact, you might not even be able to overcome this if we look at these numbers. And you can do Pythag if you want, but that's the case. Actually, no, it's not, because you're going 20. But regardless, you can point the boat wherever you want and try to generate force. And that force itself is going to combine with the net environmental force. So whatever direction you point your boat, that force vector, pretend it's here, is going to add to this force vector, the environmental forces, just like we added all the other forces, and that result is what the boat is going to do. You take all these different factors, and that's what happens. So finally, we can actually ask the question that I think we most struggle with, is where to aim the boat to go straight north, we'll say. Okay, say I aim the boat straight south. Well, this vector is going southeast, so clearly we're not going straight north. So probably stands to reason I should try to aim to the north. If I aim straight north, then I'll have a vector 0, 20. But remember, what we're doing here is finding the net effect of the boat. Is this 0, 20 plus this 6.7, negative 8.3. So what's actually going to happen is this part of the current's going to oppose you. And so you're not going to go 20 miles per hour north. You're going to go, whatever, 11.07. And this part's going to drag you off course. So your net result is going to be something like this. You're going to go off this way. So that's no good. How do you figure out what you need to do to go straight north? Well, you need to balance this out. To go straight north, you need to not go east and you need to not go west. The amount east and the amount west has to be 0. Your goal is 0 in the east-west direction, 0 in the horizontal. So you need to point your vector, your boat direction vector, somewhere into this quadrant such that the horizontal component of this, the amount of your boat going west, completely cancels the amount going east. So this should be negative 6.47 here. And then whatever, we have this too. But we don't care right now. We're just trying to go due north. So if we can balance this and this, they cancel and you're going to go straight north. We know that our boat goes at a velocity of 20 miles per hour. That's the magnitude of this vector, the length of the hypotenuse of this little right triangle we've drawn. All we need to do is produce this angle or some angle to describe what direction to aim. So I'm just going to do this one. Obviously, a better choice is probably cos-inverse. Actually, cos-inverse is perfect, because if we do cos-inverse of a negative, we get this angle, and then we're happy. So we're just going to do cos-inverse of negative 6.47 over 20, because that's telling us where do we aim the boat. I aim the boat in some direction so that this and this together make 0. Okay. Cos inverse negative 6.47 over 20 equals, let's try it. Cos inverse negative 6.47 over 20. 108.8 7, call it 100. We'll just call it 109 degrees, whatever. Now, if you want, you can just say that. It'd be nice if you turn that into a bearing. So you could call that north 19 degrees west, right? If this is not 109 and that part's 90, then 109 minus 90 is 19. That's your bearing, great. So that's where we aim the boat if we want to go straight north. Why is that the case? Well, if we break our vector into component form, here it is, 20 is the magnitude. We can put our north, south, east, west system about it. Oops. Good enough. We say we are going 109 degrees is this angle. So if I want to know the horizontal component of my vector, I simply do 20 cosine of 109. And if I want my vertical component of my vector, I do 20 sine 109. Now 20 cosine of 109 should be kind of obvious because we picked our angle so that it would come out to the thing we wanted it to be. I get negative 6.51. Yeah, that's slightly off because I'm using a rounded value, which is why I never advocate for the rounded values. Let's go back in time and redo that because I don't want to be sloppy. Okay, so 18.847. So now if we do 20 cosine of that, negative 6.47. Yeah, better. Don't use rounded values. Use exact values or store your values. Negative 6.47. Great. And then 20 sine of, let's say 109-ish, whatever, is about 18.92. So what does this mean? Well, that's what our boat's doing compared to what the dolphins and the moons and the blah, blah, blah is all doing is 6.47, comma, negative 8.93. So when we add the boat to everything else, net environment, doesn't matter what we really call it, we're saying we're taking negative 6.47, 18.92, and 6.47, negative 8.93. We add them together, we get 0, and this actually seems to be 10, which is probably a little bit of a coincidence, more or less 10. What does this mean? Okay, our boat, the actual path, so the full net result with the boat force taken account for, is our boat's going straight this direction. Delightful. It's going straight to the north, and it's doing it at 10 miles per hour. All these forces, they all just combine, and the path of the boat is 10 miles per hour north. And what's funny is your boat, if you draw the boat here, is it's actually facing this way, right? It's facing a little bit off, but because of all these other forces, the actual thing over time, the boat will go here, then here, then here, so it's going straight north when everything's all taken care of. Okay, so again, here it is. Get forces as components. We want forces as components. We want our original forces as components. We want our boat as a component. And the boat's components are, well, get the components. Add them all to get one net force. Add all your environmental things, plus, and you get the net environmental force, which is just this thing. We want to go straight north. We need to counteract the horizontal so that we balance that force out, and then we get 0 somewhere down the line because we designed ourselves to get 0, and then we only go north. We don't go east or west at all. Okay, how do we figure out where to aim the boat? Well, we said we knew the magnitude of this. Our boat force with the motor is 20. We know we're trying to accomplish this, so we have to solve for this angle theta. And if you know the inverse trig ranges and domains, that's why I got an angle here, but whatever, right? So that's how you do it. That's it. Let's do the same scenario. Let's say we got radioed in from Captain on shore. He's like, oh no, we're not going north anymore. I want to go straight to the east. Okay, so say Captain wants to go straight east. Okay, well, here's the deal. Still got our north, south, east, west situation. And the moon and the dolphins and the this and the that, right? They're still out there. Dolphins are pushing your boat. The moon's doing moon things. Okay, so here we go. That vector still exists. I want to go straight to the east. So I'd like the path of my boat to be this way. Can I just aim that way? For sure not, because then I'm going to get dragged partially south from this thing. This is pushing me east, so that'll actually speed me up in the east direction, which is delightful. I'll get there faster. But I have to counteract this. This is taking me south. If I want to go purely east, I need to counteract that by part of my velocity needs to be in the north direction. So I must aim my boat somewhere like this. Okay, I know that my boat generates 20 velocity, 20 miles per hour, so that's the magnitude of this vector. This horizontal component doesn't matter. It's going east. We like east. East is good. This vertical component matters a lot. This vertical component has to counteract this component going south if I want to go purely east, not north and south at all. So this must be 8.93 if I'm going to be able to counteract it. And so if I want my vertical force to be 8.93, and I know that my boat is going at 20 miles per hour, I just need to figure out what angle do I point my boat at so that this is true, so that 20 cosine theta equals 8.93. I would really like that to be true. Easy. Cos of theta is equal to 8.93. That's not cos, that's sine. I guess it's not so easy. 20 sine theta is equal to 8.93 over 20. Sine inverse of 8.93 over 20 is equal to the angle theta. And we're in quadrant 1, so I don't have to play any funny games with piecing together the actual angle. It all just comes out. So 8.93 over 20 is equal to theta. So guess what? In this case, my angle theta is 26 point, we'll just call it 5, we'll do 5.2 degrees. Okay, let's make that a bearing. So we actually want to go, we usually start a bearing with north, then east, we would say. So we would do 90 minus that, and say my bearing is north 63.48 degrees east. Okay, so if I want to go pure east, I go in this direction here. I generate 20 miles per hour of force. Some of that force is in the north direction. Some of it's in the east direction. The part in the north direction, if I pick my angle properly, counteracts the part of the dolphin moon current wind force that's in the south direction, and altogether we get a new resultant force. So say I want to add up and know exactly what my boat's going to do. The net boat force path, whatever, the end-to-end stage once I've picked my thing I'm going. Well, we have, of course, 20 cosine 26.52, comma 20 sine of 26.52. That's just from the boat. And then we add that to the dolphins and the moons and stuff, negative 8.93. Now, if I evaluate 20 cosine of 26.52, I'm going to get 17.9, we'll call it. Why not? So I'm just evaluating this to here. And then I'll evaluate 20 sine of 26.5. And that better be the thing that we designed it to be. It would be weird if it weren't, so that's 8.93. But of course it is, because we picked this angle so that that would be 8.93. Right, so okay, this is this. Great. Okay, so we don't need this anymore. We have decimals to work with. If we want to know what's the end result of the boat, we add the two forces. 17.9 plus 6.47 gives me a net force of 24.37 miles per hour in the east direction and a, 0 in the north-south direction, which was the point. We wanted to go purely east. We don't want to go north or south at all. So by pointing in the right direction, that's what we get. Okay. say the question is, say there's a little island. There's an island. And say here's your boat. Right? And you're pointing your boat in this direction, but the dolphins and the moon and the wind are pushing you a little bit this way. You're pushing a little bit this way. The net result is that you're going purely east. Say that island is 50 miles away. How long will it take you to get to the island? Well, if it's 50 miles away and you're going at 24.37 miles per hour, well, it should take you, divided by 24.37, about 2.05-ish hours. Okay? So what's 0.5 of an hour? 3 minutes probably? Yeah, so it takes you 2 hours and about 3 minutes. But like, it's just piecing together the information. You add vectors to see the net effect. You design your angle so that you can cancel the things you want to cancel, and then that's all good. Let's do one more. I'm going to do like this one, we used 4 forces to start. Again, does not matter how many forces are in the environment, because at the end of the day, you're just adding them and making one net force. So I'm going to do, let's just do an example with a wind and with a current. We'll just be in a boat again. So here we are, north, south, east, west. We're in a boat. We're going out on the lake, having a great time. North, south, east, west. All right, and the lake has got a current. We've got current. It's at a bearing of south 70 degrees west, and it is a 3 mile per hour current. Great, so here we go. 3 miles per hour, 20 south 70 west means this is 70, this is 20, but the better angle to call it is 200 degrees, the whole thing. Okay, voila. We want that as a component. Components are our friend. It's easy to add components. It's easy to play games with components. So zoot, what is this? The current force. So we're going to call the current force C. It is going to equal 3 cos 200, 3 sine 200. I'm not going to make that a decimal even. But great, that's the current force. Next, we'll introduce a wind force. Windy day. Let's see, the wind is at south 20 degree, no, I think it's like 25 degrees east. And let's say there's a 6 mile per hour wind. So, there's a wind this way. 25 south, 25 east. This is 25. In our coordinate system, we are much better off calling it negative 65 degrees, because then the signs come out correctly. So it's got a magnitude of 6. That means in component form, our wind vector is equal to 6 cosine negative 65, which is positive, which we want, and 6 sine of negative 65, which is negative, which we want. Okay, so let's just say those are the only 2 forces acting on our boat. Those are our environmental forces. So if our boat's sitting in still water, just floating around, well, we want the net force. We want to know what's happening. So we can take a net force, and it's just equal to the current force plus the wind force. So it's equal to 3 cos 200, 3 sine 200, they're components, and you add the respective components. You add the x's, you add the y's. Boom, boom. Add them up. I'm just putting it all in the calculator, and we're going to get a net force here. I'll put a plus for you. There's a plus. 3 cosine 200 plus 6 cosine, 6 cosine of negative 65 is equal to negative 0.283, more or less. What is that telling you? Well, that's telling you that this x component and this x component are almost canceling each other out, actually. There's not much force. The force to the left or the west is a little stronger, but overall they mostly balance. Comparatively, 3 sine 200 plus 6 sine negative 65 is going to equal negative 6.464. Okay, what does that tell you? Well, that's bigger than 3. It's bigger than 6 because both of these are pointing down, so they're enhancing the effect going down, right? Actually, I mean, that's not 100% why it's bigger than 3 and 6, but it makes sense that it's bigger, not smaller, than either of their individual parts might be. Great, that's the net force. So I can even throw out my old diagram. I can throw in a new diagram, north, south, east, west. I have a negative 0.28, so I'm going barely just a teeny bit to the left, and I'm going down. So here's my net force, okay? This is what's acting on the boat. Negative 0.283, negative 6.464. So if the boat's just in still water, it's going to be drifting a little bit to the west, and it's drifting a decent amount south. Okay, now let's say we've got a boat. Let's say we've got a fancy boat. Let's say we're on a jet ski. Okay, we have a fancy jet ski. Jet ski. And let's say this thing goes fast. Let's say this thing, we're going to take it 40 miles per hour is how fast we're going to go in whatever direction we point. And let's say we want to go purely north, right? I want my jet ski to go north. Well, what do I have to do? I have to overcome the east-west drift, which is really not that much. So I just need to point slightly towards the east, and I should be able to overcome this. This has a magnitude of 40. I can draw a little triangle here. I need to balance the horizontal component, which is negative 0.283. So I need my horizontal component to be 0.283. And then I just have to find this angle theta. Looks like cos inverse is going to be a friend here because we're trying to say cosine of theta, 40 cosine of theta, we would really like to equal this. So cos inverse of 0.283 over 40 equals theta. And this is if I want to go purely north. Cos inverse 0.283 divide by 40. And we get our angle theta is about 89.595 degrees. Yeah, like we said, this is not much force to the west. If we're going 40 miles per hour, right, we only need to be slightly off of north to get enough to counteract this tiny little current to the west. But if we want to think about the net force, this backdraft down is going to be doing a good amount to counteract our force north up. So if there's a problem that said, oh, there's an island 10 miles away, how long will it take? We want our net speed in the direction straight north. Let's say the island's up here, straight north. So we take this, and we want to combine it with this. Well, that is just 40 sine of 89.595. We want to combine it with negative 6.464, and what we'll get is the net force in the y direction, which can either be north or south, but it's going to be north. So we get 40 sine 89.595. We subtract 6.464. Voila, we get net force in the y direction of 33.535 miles per hour. North is our positive y. This is a positive value, so this is how fast we are going straight north. The island's 10 miles away, so we can take 10, divide it by that, and we would get 0.298 hours. And whatever, we can do math more or not. Okay, great. Say, oh no, we actually don't want to go north. We got to go get gas, and the gas station's directly to the east. So I need to go straight east. I don't want to run out of gas. Wouldn't want to do that. Well, if I want to go straight east, I want to make sure I'm not going south at all. I don't want my path to be like south and be like, oh crap, I got to go back north. And I ran out of gas in the middle of the ocean or in the middle of the lake. So I've got to counteract this. So how do I do that? I pick an angle that counteracts this component. The diagram's getting cluttered. Make a new diagram, doesn't take long. Here we go. I've got my net vector here. This is the current and the wind, but together they produce one net effect. The net effect in the y direction is negative 6.464. The negative effect in the x is negative 0.283. We don't care about the x. We need to counteract this y. So logically, I'm probably going to want to point somewhere this way. This step is actually not that important, which way you point, because the math will just take care of that for you. Because what we know is that we want to counteract the vertical component with our own vertical component. So this vertical component needs to be 6.464 to balance out and to let our boat actually go straight this way. Okay, so we want an angle such that 40 times the sine of that angle is equal to 6.464. We want to pick an angle to aim our boat in such that the direction in the y, or the direction towards north, south, is that magnitude. Easy. We just say sine inverse of 6.464 divided by 40. We calculate this. We get about 9.3 degrees, right? This boat's pretty strong. So even if I go a little bit off this axis, I'm gonna get enough of a counterbalance and my boat's gonna go straight this way. Again, to summarize, we start with a bunch of outside forces. It could be 1, it could be 2, it could be 0. Well, 0 doesn't make sense. It could be 1, 2, 3, as many as you want. We have a current and a wind in this case. Make them into components, because then it's really easy to add those components and get a net effect. That net effect tells you what the boat would do if it was just in still water. If you have a criteria that you want to go straight north, straight east, straight west, whatever, well, you can look at the components of this net force and you can look to balance them. If you want to go purely north or south, that means you want to go not at all east or west, so you need to balance this component, make it 0. If you want to go purely east or west, that means you don't want to go north or south, so you need to balance the y component, the north-south piece, and make it 0. And then the rest falls into place. Okay, hopefully this video was helpful. Keep at it, keep with the practice, and yeah, that's all I got. Boats in the water, dolphins. On my honeymoon in Hawaii, there were tons of dolphins. I went on a little boat trip, and there are dolphins all over the place. So they do like to come check out the boats and check out the tourists and say hi. I don't think they pushed the boat and added any force, but you never know. So there you have it. All right.